Hello everyone. Uh, let's begin our today's lecture. So before I give you the lecture, I will give you announcement. That is, today is Tuesday. Uh, we have the lecture, but for the Thursday, that is the 21st October, I'm not available uh, to give you a next lecture. So I will change it another time for the next lecture. So you and so that means the Thursday we will not give you a lecture. Okay. So I will I will give you more details about this change in the WeChat, our group of WeChat. Okay, so today let's continue to finish the first chapter, introduction of numerical analysis. Last time we have seen 4 tips for how to avoid the numerical error. And here you will see the last example, last tips. It is to use more stable algorithm. Alright, so I will give you the full screen. So you see, we are interested about such a problem that is integration in equal to the function is xn minus xn divided by x plus 5 and integrate from 0 to 1. Okay, so you will see such a problem depends on the choice of n. So what we want is to compute I20 such like this, and you will see you will see what I want to do is to use such a recursive formulation. That is, I make a addition from in plus 5 times in minus 1. Okay, so this in minus 1 is simply to substitute n by n minus 1. Okay, so now I can replace in and in plus 1 by its definition. So we can simply get this integration, and then we find that from the numerator we can we can take the common factor, that is x power n minus 1. So after that you will find from the numerator and the denominator we have we from this two term we have x plus 5. So you can cancel from the denominator and the numerator. This is the numerator and the denominator. So after this cancellation, this formula you get this simple integration, that is x power n minus 1 integrate from 0 to 1. Okay, you get this one, and then and finally you get this its result is 1 over n. Okay, so after this calculation you finally find that a recursive formula, that is in equal to 1 over n minus 5 times in minus 1. Okay, you get this one, and that means once you have in minus 1, you can use this formulation to find the in. So So you will see if I can find some initial value such as I0, and I0 is just to substitute n by 0, that is 1 over x plus 5, and this is just a log in x plus 5 for x equal to 0 or 1. Okay, so you find this is equal to log in 6 over 5. So thanks to this calculation, finally we get such a very simple algorithm. The first one, we call it algorithm 1. So it consists of two equations. The first one is the recursive formula, and the second one is the initial data. So you can see that if you substitute the I0 to here, and then here n equal to 1. So you substitute n by 1, and finally you can get I1 equal to 1 over 1 minus 5 times I0. And you can continue. You substitute here by I1, and then you get I2 and etc. So remember that I want to compute I20. So that means you can apply this algorithm and use 20 times of iteration, and finally you can get I20. So at first time you will see that it seems that it is really a good algorithm, since it is simple and easy to compute, and the computational cost is very cheap. Since at the iteration you just compute one division, one substitution, and one multiplication. So you take just 3 operations, and after 20 iterations, so totally that is 60 operations. Okay. However, I will tell you this is not a good algorithm, since after 20 iterations, it gives you a very bad result, as you have seen from this figure. Okay, so the error is the value explodes. Okay, the result blow up. So this is not a good algorithm, and you will see here from at the 20 iteration, it give us a very a large number, but the real value of I20 is such a small value. Okay, then you will ask why we get such a result. So now I will give you the reason why we will have such a result. So in principle, the reason is that the very small error at the beginning of the initial data will accumulate, and amplify, and is amplified along the calculation. So that's why finally you get a very big, very large error. So we will go to the whiteboard to show you more clearly what I said. Okay, so I hope everyone can can see this whiteboard, and let's copy. Sorry, there's something problem with my pen. Okay, so let's write this is a algorithm. Okay, so okay, so in is equal to 1 over n minus 5 times in minus 1. Okay, so I get I0 is log in 6 over 5. Okay, this is algorithm. So I will give you a formal. I will give you a formal calculation to show you why we get a large error at the end. So in this explanation, I will suppose that there is no error. There's only the only error comes from the initial data. Okay, and along the computation, we will not introduce the other error. Okay, so this is an assumption. So I will repeat. We suppose the only error comes from the initial data. Okay, and along the computation, no other error will be introduced. Clear? So with such assumption in the mind, we can now to introduce the error from the initial data. So the error from the initial data. Initial data. Okay, so we suppose that this is the I0 star is what we get from our computer, and the I0 is exact value plus some delta. Okay, this is the error. Okay, this is the error, and this is the exact value, and this is what we get actually from our computer. So now let's begin the calculation. So now you see I want to compute my I1 star. That is 1 over 1. Okay, minus 5 times I0 star. So you may see in your computer, if you apply such a algorithm, what you really have is you use such an approximation of I0, not the exact I0. Okay. So as I said from my assumption that we will not introduce the other error along the computation. So that means when you make such a multiplication, substitution, and division, there is no other error. Okay, so that means along this computation that is exact. So you will get 1 over 5 times, and here I will substitute I0 star by such a definition, that is I0 plus 5 plus delta, and we rearrange it. Okay, you get this, and you will find 1 minus 5 times I0 is nothing but the exact I1 minus 5 times delta. So from this one, you find that I1 star. You find the I1 star the approximation of I1 is equal to I1, the exact value, okay, minus some error as minus 5 times delta, okay. So you can continue to compute the I2 star, that is approximation of I2, is equal to, use again such a recursive formula. You get 1 over 2 minus 5 times I1. Remember here we will use its approximation, not the exact one. So you get this one, you substitute the I1 star as here by its approximation is I1 minus 5 times delta. Okay, so if you continue to compute this one, you will get 1 half minus 5 times I1 plus 25 delta. So this is nothing but the exact value of I2 plus 25 delta. Okay, now you find the approximate from the difference from approximation of I2 and I2 is 25 delta. So let's continue this procedure. So at last you get I20 star is equal to I20 star, is equal to I20 star equal to I20 plus minus 5 power 20 times delta. Okay, this is what you get finally. So here I20 star is the exact value. Okay, is the approximation of I20, and I20 is the exact value. This is what we want to get, and this is the arrow. Okay, and you will see this is the initial arrow. So this is small. Okay, this is very small. However, this is the factor. It is very large. Okay, very large. So now, even though at the beginning, the arrow is very small. However, you see here this factor is too large. Then that means this arrow is amplified. Okay, so that's why finally you find a very huge difference between the exact value and the approximated value. So, so that's why the algorithm A is not stable. So it is unstable. Okay, so this is not a good one. So let's go back to the slide. Okay, so do we have a way to propose a more stable algorithm? The answer is yes. We can propose a more stable algorithm like this. You see, here I propose the algorithm B, and what's the difference is instead of for this algorithm, it seems that we use a backward algorithm. So recall that for algorithm A, we need to see, it can be considered as a forward algorithm. That means you get in minus 1 and apply this one, you get in. However, for algorithm B, you get in, then you compute the in minus 1. So you may find that for the recursive formula, it is something equivalent as we have in algorithm A. Okay, so that means this is the same thing with different form. And then the objective is again to compute the I20, but this time you will use I40 as a start point. So I tell you, if you get something as I40, you substitute the IN by I40, so you get I39, and then you put I39 here, you get I38 and etc. Okay, you continue this procedure, and finally you can get I20. So here we can prove that such an algorithm is stable. Okay. So I will show you this the reason why the second algorithm called the backward recursive formulation is stable. So to show you more clearly, let's go back again to the whiteboard. Let's clean what I write here. So so you see, I get the algorithm B. Okay. So in minus 1 minus 1 over 5 times n minus 1 over 5 times in. So again, in this algorithm, I will suppose that there is no arrow at the beginning. No, sorry, there's no arrow from the along the computation, and the only algorithm comes from the beginning. Okay, so here I use I40, okay, as an initial data. Okay, this is initial data. Okay, so firstly, I give you a reason why this algorithm works. Okay, so I suppose that I40 star is equal to I40 plus some delta. Okay, I40 star equal to I40 plus some delta. Okay, this is the arrow. And then I will compute I39 star is equal to, now let's apply this recursive formulation, that is 1 over 5 times 40 minus 1 over 5 times I40 star. Yes, let me finish my explanation of why this algorithm is let me finish my explanation of why the algorithm B is stable. Then I will tell you how to choose I40. Okay, of course, actually I40 is something unknown. Okay, so continue. So as I said, we suppose that there's no error along the computation. Okay, so I will substitute the I40 by I40 exact plus this arrow delta. Okay, so you can continue this calculation. Okay, you get this one, and the first two terms together is nothing but I39 exact minus 1 over 5 delta. Okay, so you get the difference between the approximated I39 star and I39 is the minus 1 over 5 delta. So you can continue. I38 star is equal to 1 over 5 times 39 minus 1 over 5 I39 star. Okay, so similarly, you get I39 minus 1 over 5 delta, and you rearrange this one. Okay. Okay, I think this calculation is not difficult for you. And the first two terms together, you get I38 exact plus 1 over 5 delta. Okay, so you get these two things together. And what you observed from this one is that the approximated I38 star and I38 is 1 over 25 delta. So again, you can similarly find a result as the difference between I20 star and I20 is equal to 1 minus 1 over 5 power 20 delta. And you see, suppose that this is small, and this is something also very small, even small. So together you get error very small. So that's why the second algorithm is very accurate. Okay, clear for you? So now it remains the last question: how to find a good approximation I40 as the initial data. So let's go back to my slide. Okay, so here you see I write down a property for I n minus 1. So you will see I n minus 1 is just between I over 6n and I over 5n. So why this is true? So we can easily to show you this is really true. So so we can get in minus 1. This is sorry. Let's restart from this point. So you see, I get my formulation, recursive formulation is 1 over n plus 5 times I 5 times I n minus 1. Okay, this is my recursive formulation. And since you see in is nothing, sorry, wait, okay, I may write here. Remember that in is nothing but such an integration of x power n over x plus 5 dx. Okay, in is nothing but this integration, and you will find this function is something positive for x between 0 and 1. Okay, this is something positive. So such an integration is larger than 0. Okay, this one is larger than 0. So that means this one is larger than 0. Then you can find that this gives you nothing but but 1/5 times n is more than in minus 1. Okay, so you will see this inequality give you the right part of this property. Okay, so now we can prove another property at the left hand side, left part. It is this one. So why this is also true? That is because we can thanks to the definition of in, we can find I in is smaller than in minus 1. Okay, this is because this is because in x plus 5 is smaller than I power n minus 1 over x plus 5, since x between 0 and 1. Okay, since 0 belongs to 0 and 1, so you may have this one, and then you can imply that in minus 1 is larger than in. Okay, thanks to this one, I get in, sorry, 1 over n minus 5 times in minus 1 is equal to in, and this is smaller than in minus 1. So you find that finally this is equivalent as 1 over 6n smaller than in minus 1. Okay, so this gives you the left part of this property. So once you have such a property, you substitute the n by 41. Okay, you substitute n by 41. You take n by 41. You will find that this is here is I40, and here is 1 over 6 times 41, and here is 1 over 5 times 41. Okay, so you know that I40 is between these two numbers. Then you just get the average of these two numbers. That give you an approximation of I40 star. Clear? So that's why that's how I get approximation for I40. Okay, so you see. So you see from this example, to use more stable algorithm is very important. Okay, so that means each time after you design an algorithm, so try to make some analysis on this algorithm. Okay, before you use it in practice. So I think I finished the first chapter. Okay, the first chapter, and you see here, I leave you some exercise to do. Okay, you see, firstly, this is for exercise, that is to compute in. Okay, and here the n I will use 13, and for this one the procedure is very similar as what we have in the previous example here. That is for this one, they are very similar. Okay, with the previous example, and the second exercise is how to avoid the loss of significant figures. Okay, and you have three example like here, and finally you will have exercise. So we have x1 star and x2 star. They both of them have three significant figures. Then find the relative arrow bound for x1 star and x2 star. Okay, this is the total three exercise. I leave you as the homework. Okay, so this is the end of the chapter 1. Okay, so now you can try to finish this one, and then and then you can submit your homework to my assistant later. Okay, so I suppose that when I not this is not the homework one, since you can firstly to finish these three exercise yourself. Then after we finish the chapter 2, then after chapter 2 you will have the other exercise. So all the exercise for chapter 1 and chapter 2 together is your homework 1. Clear? Okay. So let's change. Yes, these slides you can download from the disk of HIT. I already tell you many times. Okay, you can download from there. Okay, you can just check announcement of our WeChat group. Clear for everyone? Clear or not? Okay, so I hope this is clear. So now we change to the second chapter. So let's begin. For the deadline to submit your homework, I don't know, maybe after 3 weeks. Since for this chapter, you see for this chapter interpolation and approximation. Okay, for this chapter, you will find that at the end. At the end, you have also many not many. You have also 1, 2, 3. You have also 1, 2, 3 exercise. Okay, so you also have to finish this 3 exercise together with the exercise of chapter 1. That is the homework 1. Clear? So maybe after 3 weeks you can submit your homework. Okay, so now you have time to finish the homework of the chapter 1. Okay, then after that so when you submit your homework, you can scan your homework and then substitute to and submit to my assistant in the WeChat group. Okay, so she will collect it. She will collect all the homework. Okay, so continue. So the name of this chapter 2 is the interpolation and the approximation. let's give you firstly the motivation. So you will see there are two kinds of problem. Okay, but the objective is more or less the same. So we have the data, as you see the right point. This is our data, and from the left figure and the right figure, the right point is the data. Okay, and what we want to do is to use some very simple function, okay, to describe this the feature of this data. And there are two ways. Okay, the first way is called the interpolation, as you see in the first block. Okay, interpolation. That means you have the data, and we want to find a very simple function that will pass through all this data. You see, we find the function which pass through all this data. This is called the interpolation. Okay. Another way is, as you see from the right figure, we have much more data compared to the right figure. Okay. You see, we have much more right point compared to the left side. Okay. So now again, we want to find a simple function that can describe the feature of this data. And this time, this function will not pass through all this data. Okay, so we will not ask this simple function pass through all this data. We just want all this data just around this function. You see, this function is just like a very smooth curve. Okay, very smooth curve, and the data is just around this curve. Okay, so the way we get this curve is called the approximation in least square sense. Okay, so don't worry, I will give you all the details to find these two kinds of function later. So you will see more example from this page, and from the top line. From the top line, you see I have 1, 2, 3, 4, 5, 6, 7. I have 7 right point, and I give you 3 figures, and from these 3 figures, they have the exact same seventh point. Okay, so these 7 points are the same, but you see, I find the 3 different. I find the 3 different function that pass through this right point. Okay, and they are not similar from each other. Okay, you see the 3 figures, they are very different from each other. So what does this mean? This means that there are so many ways to interpolate such point. Okay, and then how to choose from them which one is the best. Okay, this is a question. We will answer it later. And then for the second line, you see from the second line, we do the approximation by using the list by using the method of approximation in least square sense. So from the left one, you will find that you have many data, and then we approximate it by a straight line. Okay, a straight line. And at the right hand side and the right side, you have the data, and you approximate it by a parabolic curve. And then also there is some question how to choose this curve, and whether this curve, such a curve is exist or unique. So there are so many questions we should answer in this chapter. And then you see the outline is showing here. We will divide this chapter in three parts. The first one is polynomial interpolation. The second one is piecewise polynomial interpolation. And the third one is approximation in least square sense. So let's start from the first one. Okay, let's recall the motivation of the polynomial interpolation. There are mainly two situations we need to apply the polynomial interpolation. The first one is to find a function that describe the describe the discrete data. Okay, so that is very similar as what you have seen from here. You have some data like here, and you have no function. You don't have a function to describe them. So you want to find a simple function to describe the feature of this point. So this is just the first motivation to find a function to describe the discrete data. Okay. The second one is to find a simple function to replace a complicated function. Okay, what does this mean? This means that sometimes we know the explicit formulation of a function. Okay, so that means this function is given. Then why we need again the polynomial interpolation? It is because the function given have a word have a such complicated expression, and such a complicated expression is not easy to be used in practice. For instance, sometimes when you want to compute the derivative or the integration or other operations, if the function f is too complicated, it is not trivial to make such kinds of operations. So we want to find some very simple function. Okay, these very simple functions are very close or very similar to the complicated function, and then we can just replace the complicated function by simple function. So then when you want to do the other operations, the job will be very easy. Okay, so this is the main two tasks. So let's see. We can now make a short break, and then let's continue. Okay. Okay, everyone, let's continue. So we have just seen the motivation of the polynomial interpolation. Maybe more precisely, we see the motivation of interpolation. And in this part, we will focus only on the case of polynomial. Since polynomial is the simplest function we have to describe some data, okay, and for instance to compute the derivative or integration for polynomial is very easy. Okay, this is something basic we have learned in your bachelor. So now let's see how to define a polynomial of degree n. And it is just right here. Okay, if a function p belongs to the set of the real polynomial of degree n, then it can be written as a0 plus a1x plus a2x squared until an times x power n. Okay, this is a polynomial of degree n. Of course, all a0 to an is some constant that is a real number. And of course, if it is a polynomial of degree n, then this an cannot be equal to 0. Okay, an is different from 0. Okay, so if you want to define a polynomial interpolation function, then it should verify such a property that is p of xi is equal to yi. Okay, p of xi is equal to yi for I from 0 to n. Okay, and later we will call this is the interpolation condition. Okay, so so now you see before we find a way to give the polynomial p, we should firstly answer a question whether such a polynomial exists or whether such a polynomial is unique. Okay, and the answer is yes, thanks to such a theorem. The theorem tells that there exists a unique polynomial p from the set of polynomial of degree n, Pn, which interpolate the distinct nodes xi and yi. So that means it verify this interpolation condition. Okay. So now let's see. So to prove it, before prove it, let's see such an example. Okay, such an example is given here. We want to find a polynomial of degree 2, which interpolates the nodes minus 1, 2, 0, 3, and 1, 6. So what does this mean? This means we want to find a polynomial P2, which is under such a form a0 plus a1x plus a2x squared, such that P2 minus 1 is equal to 2, P2 0 or is equal to 3, and P2 1 is equal to 6. Okay, so you see that is 1, 2, 3. We have 3 interpolation condition. Okay, so this is the 3 function. And now, thanks to the definition of P2x, we can substitute now the P2 by its definition here. So by a simple calculation, we will find that the first equation gives you simply as a0 minus a1 plus a2 equal to 2. Okay, this is first equation give you this one. And the second equation give you just a0 equal to 3. And the third equation, P21 equal to 6, gives you a0 plus a1 plus a2 equal to 6. Okay. Now you get a linear system. Okay, this linear system consists of 3 equations and with 3 unknown. That is a0, a1, a2. So you solve it. This is something not very difficult to do. So you solve it, you get a0 equal to 3, a1 equal to 2, and a2 equal to 1. Okay, so thanks to this one, and finally you find the a2x is equal to 3 plus 2x plus x squared. Okay, so I suppose this is clear for you. Okay, this is a simple example that show you we can really find a polynomial of degree 2. Okay, with such an interpolation condition with 3 nodes. Okay, so now we can consider more general case. Okay, in this general case, we will consider Pn equal to this one. Okay, this is nothing as this one. Okay, they are the same. And now we.
Laoshi.
Yes.
Yes. Please, this is Celestina. I don't have a background on numerical analysis, making it very difficult
Can you
for
speak
me
loudly?
for
I
all this.
can't hear you very clearly.
Please, I'm saying that I don't have a strong, I don't have any background on numerical analysis. I don't
Yes.
know if there is any way you can help me better understand this whole concept because
Yeah.
I don't understand anything.
In fact, you do not have a background of numerical analysis. Since for my lecture, I only need you to know some calculus. So you just have to learn the calculus and linear algebra from your bachelor. Understand? If you never learn about the calculus and the linear algebra, so maybe in that situation, my lecture is difficult for you. Clear?
Yeah.
So you see from here, this is nothing but the linear algebra. You see, this is a linear system, and you solve it. Okay. So what we have to do is to solve such a linear system. And here, what
I don't know if your assistants can help me get the whole concept about the numerical analysis. get a little basis, then I can build on it. I don't understand anything.
You don't understand from here to here? Or from here to here?
No, from the chapter one. So I don't know if your assistant can help me
From,
get.
you say you even from the chapter 1 you have the difficulty.
Yes.
If you have such a problem, I have no solution for you. Since you see, I have many material to give you from this lecture, and I already slow down my lecture. Okay, to give you more explanation. Clear?
Okay.
So that means if you can if you want to understand more clearly for this lecture, you really have a good background of math from the linear algebra and calculus. Understand? If you have no background, a good background from these 2 points, and I think I have no way to help you.
Okay. Thank you.
Okay, since linear algebra and the calculus is not my job. I agree with me. You agree with me? Okay, so you see what I applied from linear algebra and calculus is some basic tool from these two courses. Okay, so I think for most of you, remember that you are the master student. Okay. Understand?
Okay.
So let's continue.
Yeah.
So now now you see so now let's continue. So here we will consider more general case, that is polynomial of degree n. This is the formulation, and once again you see here is the interpolation condition. Okay, you can count here. That is the first one, second one, until the last one. So if you count from the index from 0 to n, you totally have n plus 1 polynomial condition. And this n plus 1 polynomial condition is nothing but n plus 1 equation. Okay, so thanks to the definition of Pn defined here, you substitute the Pn by its definition, you finally get this n plus 1 equations here, like here. This is n plus 1 equations. And of course, now the objective is to solve this n plus 1 equation. Okay, you need to solve it. So if of course we can write it furtherly by the matrix form. Okay, so you see from here and here they are the same thing, and you will find this is a matrix. Okay, the size of this matrix is n plus 1 times n plus 1, and here is a vector. Okay, this is a vector, and this is the right hand side. So to write this the equation in matrix form from here to here. You just need to familiar with the what you have learned from the linear algebra. Okay, so I suppose this is not difficult to understand from here to here. Okay. Okay, once you get the final form of this equation, and the objective is to solve it. And from the linear algebra, a very famous consequence for such a problem is that if this matrix is invertible, okay, or in another words, if this matrix is not singular, okay, if this matrix is not singular, then this linear system provides a unique solution, that is A0 to AN. I repeat, if this matrix is not singular, okay, then it provides a unique solution, A0 to AN. Okay, how to find that? We can further denote the linear system as B times A equal to Y. Okay, B times A equal to Y. This B is nothing but the linear system, the matrix here. Okay, these matrices are denoted by B, and the A, this vector A are denoted as A, and the right hand side Y is denoted here. So I get this simple formulation of B times A equal to Y. Now I want to check whether B, the matrix B, is singular or not. So also again we have to use another property from the linear algebra, is that if the determinant of matrix B, if the determinant of matrix B is not equal to 0, then this B is not singular. Okay, I repeat that. For this matrix B, okay, a common consequence from the linear algebra is that if the determinant of B is not equal to 0, then this B is not singular. Okay, and furthermore, let's observe from this matrix. Okay, I will tell you this is a very famous matrix. Okay, it has a name. It has a name. This is Vandermonde matrix. Okay, it has a very it is a very famous matrix. This is called a Vandermonde matrix. Okay, this one, Vandermonde matrix. Okay, then then also use a consequence from the linear algebra. If B is a Vandermonde matrix, then its determinant can be simply expressed in this form. This capital pi denote as the product. Okay, this capital pi means product, and what we have is the xi minus the product of all xi minus xj is the determinant of B. Okay, from this property, you may imply that if xi is distinct from xj, okay, so that means xi is different from xj. Then we can reduce that the determinant of B is different from 0. Okay? So that means this is different from 0, and then thanks to the linear algebra, we can conclude that B is not singular. Okay? B is not singular. So if B is not singular, then we can we can find the unique solution of linear system of A0 to AN. So that means it really gives us a unique polynomial, and that means the consequence of the theorem is true, since once our nodes here they are distinct, we can find a unique polynomial P, okay, which interpolate these nodes. Clear? So this is the consequence. Okay. The theorem guarantees that such a polynomial of degree n exists and unique. Okay. So this theorem from a theoretical sense tells that we can find such a polynomial. Okay, that is in a theoretical sense. And also, let's observe again this formulation. You see, the right hand, this matrix we can construct it, and this is a dense matrix since all the elements in this matrix is non-zero. Okay, this is a dense matrix. And then the right hand side is nothing but the value corresponding to each xi. Okay, so this is known. So that means this linear system is something can be constructed. Okay, this is something can be constructed. And finally, you solve it, you can find A0 to AN. However, in practice, I want to say in practice, almost nobody use such a way to find this A. This is for two reasons, okay, as I list here. This is for two reasons. The first reason is such a matrix B is yield condition, okay. I hope you still remember what's the meaning of the yield condition. That means a small error from the data will propagate or amplified along the computation. Okay, so in that case, a method is called the yield condition. So here it is such a situation. Here is such a situation that is to say, for matrix B, if initially it has a small error, then finally you will get the result with a large error. So in such a case, B is yield condition. Then the second problem is the computation cost for the resolution of a linear system is very large, since we know that a general consequence is that to solve a linear system, if this linear system is dense, then the computational cost is capital O n cube. Okay, so it means it is very the computational cost is very large. So So, do we have some more uh, more some better way to find such a polynomial and without solving a linear system? The answer is yes. We have such a method, and such a method is named after the French mathematician Lagrange. Okay. Um, so you see, we will use the Lagrange interpolation. Okay. Uh, Before we give you the general formulation of the Lagrange interpolation, once again, let's show you a example for polynomial of degree 2. So you see, you see, we solved the same problem as we have before. We have three nodes, that is -1, 2, 0, 3, and 1, 6. Okay, we want to find a polynomial of degree 2 which interpolate from these three nodes. And this time, I will firstly introduce three polynomial L0, L1, L2 defined by here. Okay, this is L0, L1, and L2. Okay, and you see the explicit formulation is given here. Okay, and we can check a very interesting property is that for L1, L0, okay, L0, if you plot it, it is just this curve. This is L0, okay. So maybe I write here. So this is L0, okay, and this is L1, and this is L2. Okay, for L0, you can find that L0 minus 1 is equal to 1. Okay, you see, this is equal to 1. And L0, L0, 0, this here is equal to 0. And L01 is here, is also equal to 0. And then let's look at L1. L1 minus 1 equal to 0. L1, 0 is equal to 1, and L1, 1 is equal to 0. So, see, 0, 1, 0. And at last, for L2, you get 0, 0, and 1. So if you can consider this as a matrix only in the diagonal, okay, this is the diagonal. In the diagonal, you get 1, and for the other part, it is just equal to 0, okay? And you see, and you see here, we have an exercise to prove that L0, L1, and L2 they are independent. Okay. Then we will use this L0, L1, and L2 as a basis to express this P2, the polynomial P2. Okay. So here, firstly, I want to prove that L0, L1, and L2 they are independent. Okay. So so here To prove some bases are independent, we can use just the definition of independent. I make A0 times L0 plus A1 times L1 plus A2 times L2. I suppose this is 0, okay? If this can imply that A0 is equal to A1 is equal to A3 is equal to 0, then I can say L0, L1, and L2, they are independent. This is the definition of independent. And of course, this is true, since I can do such a job. I take now you see I substitute x by -1. Okay, so now thanks to this property, you see this is 1 and the other two are 0, so you get nothing but A0 equal to 0. Since this is equal to 1, and you get A0 is equal to 1. And similarly, you get A1 equal to A2 equal, sorry, this is not equal to 1, equal to 0. So you get 0. Okay, so you get all these constant A0, A1, and A2 equal to 0. Okay, so that means these three bases, they are really independent. And thanks to this property, then the set of polynomial degree 2 can be spanned by using such three bases. Okay, so then the polynomial P2x we want to find is nothing but 2 times L0x plus 0 times L1x plus 6 times L2x. Okay, this is easy to find that. If you put P2, for example, -1 here, you get 2 times L0 minus 1 plus 0 times L1x, sorry, okay, and L1 minus 1 plus 6, L2 minus 1, okay? Since this one, they are equal to 0, okay? They are equal to 0. So we get finally 2 times L0 minus 1, and this is equal to 1, so this is equal to 2. So look at here, we want to P2 pass through the nodes -1, 2, and it really, and by such a definition, it really verifies this property. Okay, it really verifies this property. Oh, sorry, this is not a, sorry, I make a mistake. This is not a 0. Okay, I make mistake. This is equal to 3. Okay, this is 3. Okay, so you find the P2 defined here really verified this point interpolation condition right here. So the polynomial we want to find is just defined by this one. Okay, this gives you the polynomial degree 2 we want. And also you can check that this polynomial is equivalent as what we have found before. So all right. So you see from this page, we get P2x is equal to 3 plus 2x plus x, x squared. And the polynomial that polynomial, okay, is equivalent as 3 plus 2x plus x squared. Okay, they are the same. Okay, they are the same thing, except that they take different form. But essentially, they are exactly the same thing. Okay, so from this slide, you can see we really have a way to define. We really have a way to define the interpolation condition, and without solving the linear system, we can find it. Okay, so in this sense, it is a better way. And the key point is to find the basis L0, L1, and L2. Okay, something given here. Once you find them, and the last step is to make some combination with the value 2, 3, 6, and then this is nothing but yi. Okay, so let's look at the more general case. So I will clean it. Okay, so this is more general case for the Lagrange interpolation. And if we can introduce a basis for Pn denoted by Lin, well, Lin polynomial of degree n, which verify the property as here, Lin xj is equal to 1 if I equal to j. Otherwise, this is equal to 0. Okay. So we suppose that we can find. Suppose that we can find such a basis Lin. Okay. So you see, in the first exercise, we give you the explicit formulation for such a basis written by here. Then the second exercise tell you that once you have a polynomial, once you can find the basis like here, Linx, then the polynomial, the interpolation polynomial of degree n can be defined as a linear combination of here. That is the sum of yi times Lin, okay, for I from 0 to n. Okay, so I think the second exercise is more or less trivial. Okay, so I will firstly give you I will firstly to check that the polynomial given in the second exercise really verify the interpolation condition. And then the next time, I will give you the way. I will show you the polynomial basis is given by this one. Okay. So let's check that this is true. So I just write here. So for example, the Pn I write xj. Sorry, I will write as xj. So by its definition, Okay, its definition is right here. So, more precisely, I can write something like y0 times L0n xj until y j minus 1 Lj minus 1 xj plus yj Lj n xj plus yj plus 1 Lj plus 1 n xj and until yn ln n xj. Okay, you see, you see from this definition, thanks to the property of the basis, if I is not equal to j, if I is not equal to j, it is such a situation you get 0. So you get 0 here to here, this is equal to 0, and this is also equal to 0 until here, you get 0. So all these things remain is yj times ljn xj. Okay, so at last, thanks to this property, when I equal to j, you get 1. So that means this is equal to 1. So you get yj. Okay. And then you see this j, I can choose them from 0 to n. Okay, so this is true for all j from 0 to n. So you see, this is nothing but the interpolation condition. Okay, so that means the polynomial defined by this one really verify the interpolation condition. Okay, so this is what we want to find. Okay, so the remaining question is how to find such a basis, and this is our first test next time. Okay, so once again I will repeat that Thursday, in 2 days we will not have a lecture. Okay, and we will see you next week. Okay, we stop here. Thank you for your attention.